Welcome to our on-demand webinar, which is titled Beyond TAR, Why Test Uncertainty Ratio, CM, which is Measurement Capability Index, is essential for modern calibration and risk management. My name is Henry Zumbrun. I'm the CEO of Morehouse Instrument Company. I had the honor of presenting this at NCSLI. If you were there, you got to see this live in person. And if you weren't there, now you can watch it on demand on YouTube at any time. The reason this is being recorded is because what was uncovered here is that most calibration labs, not all, but there's several that are still out there using outdated concepts. So hopefully we can shed some light and just awareness in regard to TAR, TUR, Measurement Capability Index, what it is, what would be the benefit from switching to like a Measurement Capability Index. There's a lot of money that's just typically wasted out there from making bad measurements. And when I say bad, for the most part, I mean risky measurements. And we'll help uncover that as we go along. So terms, always love acronyms, right? Everybody speaks them and then they never define them. Though we're going to redefine them here. And TAR, which is test accuracy ratio, is typically referred to as accuracy of the unit under test to the accuracy of the reference standard. That's it. We have the tolerance specification limits divided by the accuracy of the reference standard. It was developed by Jerry Hayes in the 1950s as part of the U.S. Navy. And what they were hoping to do is get a quick ratio to limit their risk to less than 2%. When Jerry Hayes did this, he worked, elaborated on work from Alan Eagle, Grubbs, and Kuhn, and a lot of other people. And they originally came up with a ratio of 3-to-1 and didn't feel quite right about it, so they made it 4-to-1. We'll later define what that ratio should have been to limit the PFA, which is the probability of false accept, to less than 2%. Well, let's move on. So measurement capability index is CM term that many people may have not seen. If you're in manufacturing, you probably have because you use this term more so. This is in JCGM 106. And it's defined fairly well. It's very similar to the term test uncertainty ratio, if not all but identical, which is the ratio of the span of the tolerance of the measurement quantity subject to the calibration to twice the 95% expanded uncertainty of the measurement process used for calibration. Highlighted there, you could go through this, you could pause the slide, you could read the slide. They are virtually identical in every shape, way, and form. So TAR, what we're talking about, the test accuracy ratio, has traditionally supported calibration decision rules, though it fails to account for measurement uncertainty. This can be very problematic depending on how that manufacturer designed and kind of quantified their accuracy. What we're talking about, the test uncertainty ratio, or better yet, measurement capability index, provides a better risk-based framework. And a better risk-based framework is going to, if you're doing things properly, save you a lot of money, meaning you're going to reject a lot less and you're going to ship things with confidence to your customer where you know there's not a PFA probability of false accept, meaning that you're pretty sure, better than 2% sure, that what you're sending them and the data you're sending them is correct. And when you say something passes, it actually passes. So TAR compares, as I said, the UUT and reference accuracy, but omits the key uncertainty components. And I like this cartoon we did here. This was in TR developed 1954, and we said it died in 2021. There's the ANSI Z540-1 on the person's that is crying. Why we said this, Jerry Hayes, when he invented it, he always developed it in with the sense in mind that we don't have all this computational power, and once we had better computational power, that we should use something else. So it was a very quick method, like I said, in the 50s, and people are still using it 51 years later, and it was never meant for that. It's a legacy, it's a legacy system. Legacy standards like MIL-C 45662 use TAR. They just put in numbers like 10 to 1 or 4 to 1. ANSI NCSLI Z540.1 later confused TUR and TAR. That's one of the famous rule famous not so much rumors, it's pretty much fact uh, that things happen that way. Um, but if you look at it, TAR for many champions continue to push TAR. Yeah, TAR isn't all that bad. It may still be valuable early in selecting test and measuring equipment. Like if I want to narrow things down, right? Something has a 10 to 1 and I want less risk. Maybe I choose that if I can trust the manufacturer. However, beyond using it as that tool, because we really haven't done our uncertainty, we haven't done repeatability, reproducibility, we haven't done all these other things. Maybe stability is calculated in with it, maybe it's not. Um, it's really good for that quick validation tool and maybe for some less risky measurements. There are inherent risk and flaws associated with using TAR to control your measurement risk for sure. In the 1980s, mill standard was released. And section 5.2 says, unless otherwise specified in the contract requirements, the collective uncertainty of the measurement standard shall not exceed 25% of the acceptable tolerance for each characteristic being calibrated. So what this really means is that the standard required more than just a simple 4 to 1 TAR rule that many people use. They just say, hey, I have the accuracy of the equipment, the accuracy of my standard, I'm going to do that. This standard comes out in the 80s, and it's it corresponds closer to the definition of TR, which I read earlier. And then ANSI NCSL Z540.1, 1994, calibration laboratories and measuring test equipment general requirements later replaced that standard. So digging through TR, I discovered differences, and they're pretty big differences. There's a common definition of TR, we've discussed. And then there's the NCSLI 94 handbook definition and also that mill standard definition. But accuracy of the unit under test divided by the collective measurement uncertainty, all standards used. So if I send equipment to suppliers and I have two, A and B, and I say I want a 4 to 1 TAR, what definition are the suppliers using? Are they using the ANSI Z540 definition? Are they using an older definition? This likely amounts to a risky and vastly different measurement risk from supplier A if they're using that older definition versus supplier B, which hopefully both have, calculated some components properly. Supplier A, hopefully who they purchased from did the calculation of accuracy correctly. And in supplier B's case, hopefully they calculate the measurement uncertainty correctly for their standards. But it's very distinct that when someone says TAR, and there are two definitions that are floating out there, we do not know what definition they are referencing unless they specifically say the ANSI NCSL Z540.1 1994 handbook. I know this is semantic, but this happens with TUR all the time, and it's another reason why people or JCGM 106 specifically recommends switching the language to measurement capability index, because there's not or aren't two known very distinct definitions for measurement capability index. So limitations of TAR. Ignores key uncertainty contributors. Is the measurement traceable if we haven't accounted for those uncertainty contributors? Likely not. Creates false confidence. Which is it appropriate to quantify the measurement decision risk if we don't know our measurement uncertainty? Fails modern standards, Z540.3, which I have to note is withdrawn. That was a 2006 standard. ILAC G8 ISO IEC 17025. As I'm speaking, this is a 2017 version. ILAC G8 is a 2019 version. Relies on outdated 4:1 ratio that's not sustainable. Needs explicit description of what definition to use. That's something I haven't seen anybody use ever on when they say I need a TAR of 4:1 or report measurement uncertainty or something like that. They're not giving us that definition of TAR. So very difficult in some aspects. TR offered a simple, easy to implement solution that fit the immediate needs of the 1950s. One could argue that it fit the needs through probably the 1980s till the mill standard came out. So there are things that you can say, look, let's say I'm using a micrometer to measure a shaft with a tolerance of 0.015 millimeters. If the calibration has a tolerance of 0.001 millimeters, the TAR may be calculated to be 15:1, which looks great on paper. Yet, what happens when you factor in the resolution of the micrometer or environmental changes like temperature? Likely 15:1 becomes about 1.5:1 without accounting for these significant contributors to the measurement uncertainties. You risk making a bad measurement. It just provides that false sense of security. One of the dangers of relying on TERs is it can create that false sense of confidence. When I'm at 15:1, I'm really happy, but when I do things correctly, I'm at 1.5:1, which may carry way too much risk for your application. Uh, this is something you need to decide because at 15:1, I think, the risk is, like I said, is super, super low. 1.5:1, you have a higher PFR, which is a probability of false reject, which means customers send you things and you call them bad when they're actually good. Well, that creates a whole problem for your customer base, right? Or you think you have, a super huge acceptance limit when you really don't, because 15 to acceptance limit at something that's 15:1 is microscopic. If you're at 1.5:1, it's quite large. So this is why switch to calibration measurement capability index. It compares that UUT, unit under test, some people say device under test, to 2 times the expanded uncertainty of the measurement process. Both better address traceability by including measurement uncertainty and support many global decision rules for risk-based conformity. So there you can see it broken down. The span of the tolerance, 2 times K, 95%. The CMC is your calibration and measurement capability. That K is that coverage factor, what it's reported at. Most people report it at 95% confidence or approximately K equals 2. Some might report it at K equals 3 for 99% and so on. You have the resolution of the UT included in that definition. You have repeatability, and then Z540 goes on for the denominator. The value of the uncertainty estimate should reflect the results that are reasonably expected from the use of approved procedure to calibrate the M&TE. Therefore, the estimate includes all components of error that influence the calibration measurement result, which would also include the influence of the item being calibrated, except for the bias of the M&TE. The calibration process, therefore includes temporary and non-correctable influences incurred during calibration, such as repeatability, resolution, error in the measurement source, operator error in correction factors, environmental influences, etc. Measurement capability index is a metric used in Metrology to evaluate how well measurement process or system can meet specified tolerance relative to the measurement uncertainty. According to JCGM 106, this index assesses the ratio between a given measurement specified tolerance or specification limit and the combined standard uncertainty of that measurement process. And U is the expanded uncertainty of the measurement, usually calculated at 95%. Very clear, not as clear of a definition to say CM equals T over U, the ANSI Z540 handbook, because it's here very clear, very descriptive. Like I said, both relatively are saying the same thing. It's just one's a lot more descriptive and breaks it out. So speaking a lot of this stuff, and I know you're listening to it, like what else this, I'm lost already. Well, so hopefully this example will help. I have 1,000 kgf load cell. And someone says, okay, let's look at TAR, TUR. TAR 4:1 looks fine. doesn't consider resolution, repeatability, or environmental. TUR, calibration measurement capability index, exposes these and improves confidence. So what's this is showing down here, this little red line here, is when I highlight it here, is at a really, really low resolution. Our CMMC contribution, calibration, and measurement capability is really the lion's share of everything at 99.87%. The resolution of this device is 0.13%. Total expanded uncertainty, if we're looking at it in kilograms, what this equates to is about 0.016. As that resolution increases, the CMC decreases, which makes sense. So at 0.01, resolution is now 11.52. Does it expanded uncertainty change too much? Not really. But as you keep going on at 0.2, now resolution is more than dominant. 0.5 more than dominant. 0.2, start looking at these numbers. Resolution's 34% of the budget. And if we go to one count out of 1,000, resolutions, almost my entire uncertainty budget is composed of 99.92%, where the calibration and measurement capabilities only 0.08. So when we look at the contributors to uncertainty and the weight of each contributor, basically that resolution, as it gets coarser, it becomes more dominant. Hopefully that makes sense. So the simple explanation is, if we didn't have to account for any of this, we could use a ruler to calibrate a gauge block. Not much resolution on a ruler at all, but you could say, hey, it's perfect. Everything's perfect. So really coarse resolution does not show a lot of deviation, a lot of measurement error with repeated measurements, and therefore tends to bias the results towards not being able to tell. So another graph here, resolution significantly increases measurement uncertainty. You can see here, as resolution becomes coarser, risk increases. Ignoring it in TAR-based evaluation leads to incorrect fail. So this is what happens. Manufacturers say, hey, the resolution is the same as the accuracy, blah, 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 blah. And all of a sudden you have instrumentation that when you switch to measurement capability index and other things, you cannot pass. ILAC P14, this is a policy document. And it basically, if you're a calibration lab, you know about it. It's basically states contributions to the uncertainty stated on the calibration certificate shall include relevant short-term contributors during calibration and contributions that can reasonably be attributed to the customer's device. Where applicable, the same uncertainty shall cover the same contributions to uncertainty that were included in the evaluation of CMC uncertainty component, except that the uncertainty components evaluated for the best existing device shall be replaced with those of the customer's device. Therefore, reported uncertainties tend to be larger than the uncertainty covered by the CMC. Basically saying, hey, whatever you're using for your calibration and measurement capability, you need to use the short term, like resolution, repeatability, need to be used in here. It's the formula ANSI Z540.3 handbook covers that very well with that denominator definition. So why am I presenting this? Why must the industry shift? Look, this calibration measurement capability index reduces risk in almost any application, including aerospace, medical, pharma. Think about what sector you're in, oil and gas, anything you're doing. If you calculate uncertainty correctly, you can calculate your PFA, probability false accept, PFR, your type 1, type 2 errors, other names, lots of other names for it. This, if you can do that correctly, that drives cost savings and yield improvement. And even more, I was on the podcast, NAPT's podcast with Howard Zion and Charles Ellis. Thrilled to be on that. You can, if you're listening to this and want to go check that out, that's cool. But Howard Zion wrote a paper, TAR versus TUR reasons to upgrade. And I'll read what he said. It's great. An even more compelling reason to move to TUR and specifically uncertainties is this enables anyone affected by false accept, consumer risk, or false reject, producer's risk condition found within the indeterminate range to quantify the risk and understand how it affects the measurement. So There's a lot of cost savings involved in that. This just shows why TAR is not sustainable. If I start with a process measurement down here and I say I need to go up to the national standard or need to trace this back to SI, that's at the top. Maybe people say I need to go traceable to NIST. Nothing's traceable to NIST. It's traceable to an NMI through, traceable to SI through an NMI under the mutual record. In any regards, if I start at one, then the next person, the next lab that's performing my calibration needs to be 4 times better. The lab above them, 16 times better. Lab above them, 64. Then NIST would need to be 256 times better. And then traceable back to the SI when you derive everything would need to be 1024. That is just not sustainable whatsoever as far as 4-to-1 ratios. If I do the measurement uncertainty, the TUR measurement capability index, and I start with SI measurement at 005, every time I go down this pyramid, it gets larger. I just add the uncertainty of the reference. I add my other contributors. NIST does such a great job. They have really low uncertainties. Then a reference lab may send their stuff to NIST. Guess what? Over here, their uncertainty grows. Every lab, it's metrological traceability. The documented procedure, right? It's measurement uncertainty data is cumulative from one level of the hierarchy to another. So a documented chain of calibrations, each contributing to the measurement uncertainty, is what we have on the right. So, which that is the definition of metrological traceability. If we start looking at cost and the impact here, so I go out, I'm running a company, and I have to test resistors. And I have all these, the sales guy comes out and he says, all right, I got this great resistor. I got this great meter. We'll call it the Acme Standard. It's going to cost you $6,000. You're in purchasing. You say, well, if I compare all these meters, this one's 4405, the low buck. I doubt it. The salesperson's telling me the 6,000 definitely better. Bronze is over twice the cost. And then this gold is over 3 times the cost. I'm probably sitting there thinking 6,000 sounds like a pretty good deal. Start looking at specifications. Maybe there, who knows what I need to test. This one all of a sudden is 2.5 times better than what I need to test. If I don't know any better, maybe that seems really good, right? It's at least 2.5 times better. Running these actual numbers, if I run a sample lot of per month of a lot of instruments, right? And I just look at the yield. This is telling me that I'm going to falsely accept on both of these meters 1,000 overall meters. And then I'm going to falsely reject 9,611. What that means is that I'm saying 9,611 units are bad when they're actually good. That has an inherent cost with it. My production cost to run the lot of resistors, the thousands upon thousands of resistors that I'm running, is the same, right? It could be 100,000 resistors, and I'm accepting falsely because I'm guard banding and doing other things. I'm falsely accepting 1,000, and then I'm rejecting 9,611. That is a large number. So out of the 1.35 million, if you just run numbers, you put in your own numbers, but you can say, all right, there's a cost for rejection. And do I just throw them away, or do I pay somebody to then retest them? So if I just throw them away, I'm losing about $130,000 a month. If I pay somebody to retest them, it's costing me additional $336,000 and change per month. Looking at all this, My cost then balloons for my 100,000 resistors from 1.35 million, if I want to retest them, to 1.86 million. Increased cost as percent budgeting. So it's costing me 34.53% more on the resistors. Likely yield, 90.39. Likely production rejection rate, 9.61. Looking at all these numbers, those that are manufacturing will know, if I'm rejecting 9.61, that is a large percentage. Uh, is it not? So, and if my yield is 90.39%, that's the inverse of it, pretty easy to calculate. Uh, Not too good, especially if I'm competing against somebody that went and bought this Acme Gold. If we could look over here, I paid roughly 20,000, let's just say 20,000, $19,429 for the indicator, 3 times more up front. But with the better indicator, the increased cost, if I want to retest and do everything at 0.1%, my yield is 99.97%. Looking at all of this, I might want to throw my resistors away. Maybe I don't. I don't know. But in any case, this person that bought the better indicator, you can see that they're relatively spending less than $1,000 a month or $1,300 a month, where the person that ended up buying the $6,000 indicator is spending over 500, right, around $500,000 total, like 464,802.22. So difference in equipment cost, this could just be a 1 month saving, could be $13,492. And the difference in testing monthly in this scenario would be the 464,802.22 for the period of question. If this were a monthly production yield, you can do the math, multiply it by 12. Huge numbers, right? We got like 5 million plus dollars. Just and you could have avoided all these extra costs by buying the better indicator. Really interesting as far as things go and what people buy and why they make the decision. If it's me and I see this graph, I'm buying the gold indicator, right? Accounting may have a fit up front that I'm spending the extra $13,492, but just my production yields are going to outpace whoever bought that other one. I'm going to sell more product, I'm going to retest less product, and I'm going to make overall a lot more money. Or I can get a competitive advantage because I can manufacture things cheaper and secure the contracts. It goes on and on. Willingness to pay. Maybe I don't have to even sacrifice any quality, um, any of my margin on this because my customers' willingness to pay has gone way up because guess what? They know they're not going to have the headaches associated with a bad product with these low numbers. Because you can pass, as soon as you pass those bad products to them, they put them somewhere. And then something fails and they have the recall scenario and then they pay a lot of money. So they could save a lot of money by having more confidence in what you're supplying them and buying something that actually passes. So impact over. This one, yeah, like look, this is something I ran on force equipment. So we sell this product called a BCM, and I made up some numbers here. Not made up numbers as far as these go, but basically saying the goal is 0.1% is what the accuracy of something is. So if I want something with 0.1% accuracy, I buy this BCM. This is a benchtop calibrating machine. Typically, when we put load cells in it, we can get the customer of that ratio, the measurement capability index ratio, about 2 to 1. They might get lucky and get a 3 to 1. I'm being very conservative here. With a universal calibrating machine, they're probably going to get 3 to 1. If they have automated, they could get 4 to 1. But just looking at this price tag of ownership, you can see extra cost per year for this equipment. And look, It's total cost of ownership. Every hour you spend waiting for equipment, redoing work, or sorting out quality issues is time you're not making money and potentially harming your reputation. Every wrong decision can result in unnecessary costs, extra analysis, and even potential recalls, all due to bad decision from using equipment or suppliers with high measurement uncertainties. That BCM that I'm showing on the far left, that may be the best piece of equipment that you can get, right? It may not be a $13,000 like the Acme Gold in the other example. It might be fine for what you're doing. It's certainly fine more than likely if you want to calibrate things to point two, but if you want to calibrate everything to point one, maybe the UCM is going to give you less false rejects, which is your extra cost per year. We haven't even talked about PFA here. This is just your internal cost. How much am I going to reject? And then I'm going to tell my customers that their equipment was bad when it was actually good. So that's not good either. And then very little if you get to like an automated UCM 4-to-1, and dead weight will get you like next to none. So let's look at this. I like a program called SunCal. We can run these curves of PFA, PFR. At a low TUR 1.2, your PFI is very high, starting near 40%, at 50% intolerance probability, and rising towards 70% at 90% intolerance probability. That's these numbers right here on the bottom, intolerance probability. So this means more than half of good auditors would be incorrectly rejected. At a TUR of 2.0, PFR is still significant, about 25 to 35%. At a TUR of 3.0, it drops to 15 to 20%. And then when your TUR measurement capability is small, the measurement is relatively noisy versus the specs. So to meet intolerance probability target, the rule pulls the pass limits well inside the spec. That crushes the chance that an out of tolerance item sneaks in or through, but basically you're not sending out anything that you call good that's actually bad. That's what that means. But then you pay that's this side of the equation, but then you pay on the PFR side of things. So you're rejecting a lot more. You're adjusting things that do not need adjusted. So that's what happens at a measurement capability index of TUR, basically this 4 right here. Sorry for so many. I decided to use red. These lines, the 4, that's that purple line down here, and then that dark orange line down here. If we're looking at TUR's measurement capabilities of 4 and 4.6, becomes really small, PFR approaching 0% at 4.6. Remember when I said earlier that magic number? Well, the magic number is really 4.6. If you can get something that's 4.6 times better, your PFA shrinks well less than 2%, and your PFR also shrinks. So that's generally the rule if you can do it, and if you can afford it. It's that ultimate cost balance. But if you're looking at something like it's a difference between $5,000 to $6,000 between a BCM or like a UCM in the K-Force machines, the 2-to-1 to 3-to-1, you will increase, you'll reject probably on average about 20% less. And what's that 20% worth time-wise for that extra cost? These are things you have to figure out. Started with a resistance example of just resistors batch manufacturing and went to a force example where it all depends on the tolerance you're working to and the equipment you buy. You could say, I want the very best. Well, the very best are dead weight machines. A £1,000,000 dead weight machine, if you needed to go that high, is probably $10 million. Whereas a £1,000 dead weight machine, a lot less money than that, probably $150,000, right? The 10 million is a huge number. 150 might be too much. 10,000-pound dead weight machine, maybe that's 450, 500,000. The BCM might be, a 20th of that. So you start looking at these numbers and looking at what you're going to do and the cost of things. You just have to run them all. I love this drawing for all of this because this shows everything, right? When I have the correct accept, deal with the manufacturing world, right? Conforming and non-conforming, right? Intolerance for conforming, out of tolerance for non-conforming. When I accept properly, my item is conforming and I accept it properly with a high TUR of greater than 4.6 to 1. Decisions are greater than 98% correct, giving you a confidence good equipment is accepted with minimal risk. When other side of this, when it's non-conforming, a low TUR increases false accepts, letting bad equipment pass. This leads to asset failures, recalls, and reputation damage. This is what almost everybody tries to avoid at all cost, right? They will guard ban, they will shrink the acceptance limit, and then what will happen when they do that? Typically, what will happen is this column. They will incorrectly reject things, and now they will take on the unnecessary rework, wasted time and money, and that low TUR measurement capability creates noisy measurements that create high false rejects. If we make the right decision, we do the proper fixes, we're actually rejecting something that's actually bad. So then we adjust it, fix it, send it back to the customer, do the right work, and now we're proper rework. And on the conforming side, everything's mission ready, good to go. Hopefully that all makes sense. The conclusion for me, at least, is that TUR, not a good metric. The last few slides I showed you all use measurement capability index. TAR just does not account for all the components of uncertainty correctly. And your modern measurement really demands for your cost savings, your type 1, type 2 errors analysis, everything else, production yields, that you switch to measurement capability index. And for confidence, compliance, and competitiveness, like I said, hopefully I demonstrated the case for everybody. And for anybody that's out there that's a naysayer, let's go back to 1950s where George C. Scott, I don't know how many people will recognize George C. Scott as a doctor who smoked Camel cigarettes, but not one single case of throat irritation due to smoking Camels. Remember, cigarettes were said to be good for us. Not the same as TAR, because TAR was a stopgap solution. Cigarettes were never a stopgap solution. They were just something that always put tar in your lungs and eventually gave you cancer, likely. Um, so that's it. Hopefully, all of this makes sense. And thank you for listening.